Have you ever really stopped to think about how our planet stays warm? We always hear it's like an atmospheric blanket, but what does that actually mean? Well, today we're going to shrink way, way down to the molecular level and see how a simple little wiggle is responsible for warming our entire world.
Right. So we've all heard the blanket analogy for the atmosphere. It makes sense, but it's obviously not woven from wool or cotton. So how does this invisible shield actually trap heat? What is the secret ingredient woven into its molecular fabric? That's what we're here to figure out.
So to kick off our investigation, we've got to start with something really basic, a universal truth, the relationship between energy and matter.
Okay, this is a core idea you probably remember from science class. Temperature, whether it's in a pot of boiling water or just the air around us, is really just a measure of how much molecules are moving around. So more heat means more energy, which means more movement. Simple enough, right? Let's just hang on to that idea.
All right, now that we know what heat does to molecules, it makes them move, let's meet the main characters in our story today, the molecules that make up the very air we're all breathing right now. So first up, we've got oxygen, or O2. This is one of the heavy hitters, a huge part of our atmosphere. Now, look at its structure. See that? It's just two oxygen atoms, and they're bound together really tightly. It's simple, and as you'll see in a minute, that makes it pretty rigid.
And here's its partner, nitrogen, N2. This guy is the most common gas by far. And just like oxygen, it's a simple two-atom molecule, also bound together very tightly. In fact, between nitrogen and oxygen, you're looking at about 99% of the air. But here's where it gets really interesting. It's not the big players, oxygen and nitrogen, that have the most important job when it comes to warming. Nope. It's the other guys, the trace gases that exist in tiny amounts, that have this very special talent. For example, take a look at carbon dioxide, or CO2. You can see right away it's just built differently. It's got 3 atoms, a carbon in the middle, with 2 oxygens on the side. That structure gives it a bit more complexity. And check out this one, methane, CH4. It's got 1 carbon atom bonded to 4 hydrogen atoms. It's even more complex, kind of like a little pyramid. So these molecules, they're not simple and rigid like oxygen and nitrogen, and that little difference, well, it changes everything. Okay, now we're getting to the heart of it. We're about to see what happens when energy rising up from a warm Earth bumps into these different types of molecules. This is what I call the great molecular wiggle.
This is the key question, right? Does that heat energy affect our simple, stiff molecules like oxygen in the same way it affects our more complex ones like carbon dioxide? Let's find out.
And boom, here's the answer. This chart splits our cast of characters right down the middle. In one column, we've got our wigglers, like carbon dioxide and methane. And in the other column, we've got oxygen and nitrogen, the ones that, well, just don't wiggle much at all.
So why? What's the difference? It all comes down to how they're built. The simple 2-atom structure of oxygen and nitrogen is really rigid. So when energy hits them, it's like throwing a pebble at a brick wall. It just kind of bounces off or goes right past. But the more complex molecules like CO2 and methane, they have bonds that can bend and stretch. They're flexible. So when energy hits them, they absorb it and start to vibrate or, wiggle. So this wiggle is the crucial piece of the puzzle. But you might be thinking, how does a tiny vibrating molecule warm up an entire planet? Well, let's connect those last few dots. Okay, step 1. Picture a little packet of heat energy rising up from the Earth's surface. It shoots up and runs into a nitrogen or oxygen molecule. But since we know those guys are rigid, the energy just passes straight through, continuing on its journey out to space. No drama, nothing happens. Now let's run that back. Same packet of energy leaves the Earth, but this time it bumps into a molecule of carbon dioxide. Because this molecule has those flexible bonds, it doesn't just let the energy go by. It catches it. It absorbs that energy. And that new jolt of energy sets the whole molecule vibrating like crazy. And this right here, this is the final and most critical step. The molecule can't hold that energy forever. It has to release it. But, and this is the absolute game changer, it doesn't just fire it straight up towards space. It shoots that energy back out in a totally random direction. Some goes up, some goes sideways, and, crucially, some of it goes back down towards Earth. And that is the energy that gets trapped, warming everything up. So now we can finally put all of these pieces together. What we've just watched, on a molecular level, is the engine that drives the entire greenhouse effect.
This gives us a really solid working definition. A greenhouse gas isn't just any gas. It's a gas with that special, flexible structure that lets it do this three-step dance. Absorb heat coming from Earth, vibrate with that new energy, and then release that energy back into the atmosphere. So, to sum it all up, these special greenhouse gases absorb heat that would otherwise just be lost to space. Then they send some of that heat back down, warming the atmosphere. And let's be super clear here, this is a completely natural process, and it's absolutely essential. Without it, the Earth would just be a frozen, lifeless rock. And this is the question that brings all of this science into our world today. If a nice, thin blanket is good and keeps us comfortable, what happens when we start adding more and more layers? The more of these wiggling molecules we have in the air, the more energy gets caught and re-radiated back down, basically thickening that atmospheric blanket and causing the whole planet's temperature to rise. So we've seen the mechanism, we get the physics, and we know that the concentration of these wiggling gases, like carbon dioxide, is going up. That leaves us with the final, massive question. Is the change that we're seeing right now just part of a normal cycle, or is it something else entirely? But you know what? That's a huge investigation for another time.